Today we will look at a simple mathematical model for an ecosystem, because we want to find out what happens to a population of animals in a forest. To study the long-term behavior of such a system, we need its eigenvalues. To visualize the effect of a linear transformation, I've been using this grid of dots. The grid is rectangular, so that you can clearly see that straight lines always remain straight and evenly spaced. It also makes it easy to investigate what happens to the unit square. But there is a completely different way of looking at the effect of a linear transformation. In this video and the next one, we look at circles and how they are transformed. The rectangular and the circular view give you two different perspectives on the same transformation, and they uncover different intriguing properties. What we will discover is that all linear transformations transform a circle into an ellipse. All of them. Even a rotation turns the circle into, well, itself. And that's definitely an ellipse. And a projection pushes the circle into a line segment, which is a very, very flat one-dimensional ellipse. It's quite amazing that any linear transformation you can come up with, no matter how peculiar, always produces ellipses, or ellipsoids in higher dimensions. If you're intrigued and you want to understand how and why this happens, there are two matrix decompositions you need to understand. In the next video we will look at the singular value decomposition, which tells us exactly where all those ellipses are coming from. You can already watch that video on Patreon right now. We would be extremely grateful for your support. But in this video we first have to get comfortable with a more specific case, the eigendecomposition, which basically talks about diagonal matrices. Let's look at a familiar diagonal matrix first. It stretches the x-coordinates by a factor of 3. And the y-coordinates by a factor of 2. Remember to always look at the shape of a matrix to figure out its effect. The elements on the diagonal tell you how each axis acts on itself. The elements of the diagonal tell you how the axes act on each other. Since those numbers are all 0 here, there are no such cross interactions. The value of the y-coordinate has absolutely no influence on the final x-coordinate, or vice versa. You could say that our matrix is decoupled into two completely separate parts, one that involves only x and one that involves only y. This is extremely useful if we have to solve a complicated system of equations. If we can somehow manage to transform it into a diagonal system, the equations become trivial to solve, because each of them contains only a single unknown. The system falls apart into independent equations. That's what the word decoupling means. One big limitation throughout this entire video is that diagonal matrices are always square. For rectangular matrices, we will have to find a more general approach in the next video. Here's a matrix that clearly isn't diagonal. It has this slanted stretching effect on the vectors in the 2D plane. How can we make it diagonal? And is that even always possible? Well, check out this line here. As I perform the transformation, you'll notice that the vectors on this line just scale by a factor of 3. They do not move away from the line. The line goes through the origin, so it's a linear subspace of the two-dimensional plane. That's because the sum of two vectors on this line also gets scaled by the same factor of 3 and stays on the same line. The 0 vector itself also gets scaled by the factor of 3, so it stays on this line in a trivial way. And so we conclude that these kinds of lines will always run through the origin and they will always be linear subspaces. Here is another line with the same property. This time, the vectors don't even get stretched at all. They just stay put. the transformation has absolutely no effect on them. Vectors that stay on their line are called eigenvectors. The factor by which they get stretched is called the eigenvalue. So the vectors on this line are all eigenvectors, and their eigenvalue is 3. And the ones on this line have an eigenvalue of 1. If I give you an arbitrary matrix like this one, how do you find its eigenvalues and eigenvectors? Well, there are basically 2 ways. One way is the visual approach we just used. You stare at the transformation long enough and you try to spot the lines that don't change. This isn't always easy, but like I said, you can switch to a circular view to see things more clearly. What I will do is plot a large number of vectors on this circle, and then I will connect them to where they end up after the transformation. This new picture clearly shows that most of the vectors get transformed away from their original line through the origin. But there are a few, such as this one and that one, that are transformed almost in the same direction. So these would be very close to the actual eigenvectors. You can then zoom in and refine the approximation. If you're not looking for the exact solutions and you just want to get a good feel for where they are, this intuitive approach might be good enough. The second and more precise approach to finding the eigenvalues is to use algebra. I won't spend too much time on the precise calculations, because you can already find them elsewhere. Basically, you want to find the solutions to this equation. The matrix A is given. This is the matrix whose eigenstuff we want to find. We're looking for vectors v so that when you transform them, by multiplying them with A, the result is just a scaled multiple of v itself. We don't know the v's, the eigenvectors. And we also don't know the scaling factors, the eigenvalues. In order for this equation to have a solution, the determinant of the matrix A minus lambda times the identity matrix must be 0. For a 2 by 2 matrix A, that gives us a quadratic equation that we can solve to find the eigenvalues lambda. For a 2 by 2 matrix that contains generic letters instead of specific numbers, this leads to the following quadratic equation. The 2 solutions of this equation are the eigenvalues lambda 1 and lambda 2. Maybe you remember learning in school that the constant term of a quadratic equation is the product of the solutions, and this coefficient is their sum. But you may also recognize these expressions as the determinant and the trace of our 2 by 2 matrix. That's pretty amazing. It means that the product of the eigenvalues is the determinant, and their sum is the trace. For a diagonal matrix, this is obvious. The eigenvalues are on its diagonal, so the sum of the eigenvalues is clearly the trace. You can also easily verify that the product of the eigenvalues is the determinant. But our generic expression shows that this is true for any 2 by 2 matrix. And in fact, it even holds for any n by n matrix as well. I mentioned before that the determinant behaves like a product, and the trace like a sum. Here we find that they are literally the product and the sum of the eigenvalues. If you want more details about how to calculate eigenvalues, or if you want to see how it works for a 3 by 3 or a larger matrix, check these links in the description. Now you're probably thinking, hang on a minute, a quadratic equation doesn't always have solutions. What if the discriminant is negative? Well, that means that the eigenvalues will be complex, so you won't be able to find any vectors that stay on their lines. The most obvious example is a rotation. When you rotate the plane, every vector gets moved away from its original line. Except for the origin, of course, but that's always gonna stay in place, so it isn't very interesting. Here's a 90-degree rotation. If you solve its quadratic equation, you find that its eigenvalues are indeed complex. They have the values I and minus I. So you could say that you still have eigenvalues, but they are imaginary. You could even say that scaling a vector by the value I has the effect of rotating it 90 degrees. Whenever rotations are on stage, complex numbers are always hiding behind the curtains. In 3D, when you rotate around an axis, the vectors on that axis don't rotate at all. They stay in place. So they are eigenvectors with an eigenvalue of 1. The other two eigenvalues are still complex. I think it's interesting that you can basically use the concept of eigenvectors to find the axis of a 3D rotation. To get a strong intuition for all this eigenstuff, let's look at some more examples. This matrix has the same number on its diagonal twice. Geometrically, it scales vectors uniformly by the same factor in all directions. What do you think it will do to this circle? Right, it just stretches it out, but it stays a circle. This means that all vectors in the plane are eigenvectors, because they all stay on their line. A specific example of this is the identity matrix, which scales all vectors by a factor of 1. Another example is a rotation over 180 degrees. It scales all vectors by -1. So these are examples of matrices whose eigenvectors cover the entire plane. Next, let's look at a reflection. Try finding the eigenvectors visually first. Can you see two lines where the dots stay on these lines? Well, the first one is the reflection line itself. The dots don't move at all, so they have an eigenvalue of 1. The other eigenline is orthogonal to it. The vectors on this line get flipped across the origin, so their eigenvalue is -1. If you can't immediately spot these lines, you can always check the unit circle. But of course, you can also just solve the algebraic equation. I want to show it explicitly here because it contains a few surprises. For a reflection over an arbitrary line that makes an angle theta with the horizontal, you can construct the corresponding matrix by using the trick I showed you in the previous video. Then you subtract lambdas from the diagonal elements as usual, and you write out the determinant. It's the product of the diagonal elements minus the product of the other two. The first surprise comes from trigonometry. This expression here simplifies to 1 for any angle theta. The resulting expression no longer contains theta. So the exact direction of the reflection line makes no difference as far as the eigenvalues are concerned. The second surprise is that this equation is exactly the same as the property for reflection matrices that we discovered earlier. A reflection matrix satisfies r² equals 1, because two reflections over the same line cancel each other out. And now we get exactly the same equation for the eigenvalues. The solutions to this equation are 1 and -1, as we expected. But I bet you didn't expect these equations to be identical. If you want to get a deeper understanding for why this happens, you can look at the video that I've linked in the description. Now, here's an important warning. You may think that this line is also an eigenline. These dots all stay on their line, so they must also be eigenvectors, right? No, not at all. Please remember that in this visualization, each of these dots is just the endpoint of a vector that starts at the origin. This vector over here, for example, gets transformed up at an angle. It doesn't stay on its line at all. You always have to look at the entire vector, from the origin to its endpoint. It also helps to remember that the eigenlines must always go through the origin. Here's another cool example. A projection onto a slanted line. Can you spot the two eigenlines just by looking at the moving dots? Well, first of all, the dots on our slanted line stay in place. The projection doesn't have to do anything to them because they're already on the target line. So they will all be scaled by an eigenvalue of 1. And then there's this line in the direction of the projection. What happens to its vectors? What factor do they get scaled with? Think about it. The factor must be 0, right? That's how they all end up at the origin. So whenever you have an eigenvalue equal to 0, the eigenvectors in that direction will all be shrunk down to the origin. This means that the 0 eigenvalue can help us find the null space, also known as the kernel. That's another useful thing that eigenvalues can do for us. Again, you can solve the quadratic equation to verify that the eigenvalues are indeed 0 and 1. And as before, this equation is exactly the same as the algebraic property of a projection that we talked about earlier. P squared equals P, because projecting twice has the same effect as projecting only once. There's another interesting and important thing you should notice here. One of the eigenvalues is 0. The vectors along this line get squashed to a single point. This causes the transformation to lose information. It loses an entire dimension. It takes us from 2D to 1D. We already saw that this is why such a transformation cannot be inverted. Its determinant is 0 because it reduces all areas to 0. But now you can also explain this in terms of the eigenvalues. The determinant is the product of the eigenvalues. So as soon as even a single eigenvalue is 0, the entire determinant is always going to be 0. It's nice to see how all these different explanations come together and reinforce each other. Okay, how about a few non-geometric examples? Here's the permutation matrix. Finding its eigenvalues is tricky, because we can't use our geometric intuition this time. But I can tell you that this vector, with all 1s as its elements, is an eigenvector for any 4x4 permutation matrix. Can you see why? Think about what happens when the matrix transforms the vector. It permutes the elements, shuffling them into new positions. But since the elements are all the same, the shuffling doesn't make any difference. So we have found an eigenvector which is totally immune to any effects of the permutation. Its eigenvalue is just 1. We'll talk about this example again in an upcoming video about matrix representations. Here's another very important example. The derivative. I showed you earlier that you can write it as a matrix. But here I just want you to think about it as a linear transformation on functions. Can you think of an eigenfunction? In other words, is there a function that simply scales by some factor p when you take its derivative? Think about it for a minute. This equation has a very famous solution. It's the exponential function. When you take the derivative of the exponential function, you just get the function itself, with perhaps a constant factor at the front. So the exponential functions, for all possible values of p, are the eigenfunctions of the derivative operator. There are infinitely many of them, one for each value of p. Great, so we now have a pretty good idea for how to calculate the eigenvalues and find the eigenvectors. But we still don't know how to make a non-diagonal matrix diagonal. That's what we'll do now. Look at this example again. We found two eigenlines. Vectors stay on these lines after the transformation. So if we could somehow use these two lines as our new x and y axes, we would have a transformation that stretches along one axis by a factor of 3 and along the other by a factor of 1. That's exactly what we want. So the key observation is that we should change our basis. our new basis vectors should be a pair of eigenvectors, one coming from each eigenline. In this new basis, everything along the first axis becomes a pure scaling by a factor of 3, and everything along the second axis becomes a pure scaling by a factor of 1. There are no more cross terms or interference between the axes. They are completely decoupled. And so in this new basis, our matrix becomes diagonal. This new basis is called the eigenbasis. I hope you've watched the previous video, where I explain how to do a basis transformation using a sandwich product. You have to put the new basis vectors into the columns of a matrix P, and then sandwich your original matrix between P and its inverse, like this. We want the new basis vectors to be the eigenvectors of our matrix, so we put those in the columns of P. Et voilà! This is how you diagonalize a matrix. This is called the eigendecomposition. We have decomposed our non-diagonal matrix into a product of 3 parts. 1 part diagonal and 2 parts basis change. Now you actually have some wiggle room here. When putting the eigenvectors into the columns of P, you can choose the order in which you put them. This makes very little difference. It will just switch your axes around, causing the diagonal elements to appear in the opposite order. In practice, you will often see that people prefer to order their eigenvalues from largest to smallest. But this is not such a big deal. I just thought I'd mention it. When 2 matrices represent the same transformation but in a different basis, we say that the matrices are similar. So our original matrix is similar to the diagonal one. Similar matrices always have the same eigenvalues because they represent one and the same linear transformation. The converse is not true, however. For example, these 2 matrices have the same eigenvalues, but they are not similar. When 2 matrices have the same eigenvalues, they obviously also have the same sum and product of eigenvalues. So they always have the same determinant and trace. For the determinant, you can understand this geometrically. The determinant tells you the factor by which all areas get stretched. This doesn't change when you move to a different basis. For the trace, this result doesn't have a clean geometric interpretation that I'm aware of. The main goal of the eigendecomposition is to decouple a linear system into simpler parts. But there is another, less obvious application that I want to show you. There's a forest far away, where unicorns and trolls are fighting for their survival. As a professional biologist, you have been studying this delicate ecosystem for decades, and you have assembled your findings in a mathematical model. Every year, the number of unicorns U and the number of trolls T can be calculated from the counts of the previous year. Now, I should make it clear that unicorns are absolutely vicious creatures. They spend their entire day hunting down trolls in order to eat them for breakfast, lunch, and dinner. So this coefficient means that without any trolls to eat, the number of unicorns would fall very rapidly. And without any unicorns, the trolls would absolutely thrive. But there are also effects between the 2 species, and those effects are given by the numbers of the diagonal. When there are many unicorns, they start eating all the trolls, and the value for T goes down by quite a lot. And when there are many trolls, the unicorns can survive on a richer diet, so they may have a better chance of surviving. After putting these numbers in a matrix, we can watch our little ecosystem play out over time. The number of unicorns is on the horizontal axis, the number of trolls on the vertical. Each year we multiply all vectors with our matrix, and we do this year after year until we start seeing a long-term trend. It seems that the system is moving towards this line. The question is why? And why this specific line? The answers to these questions can be found in the eigenvalues and eigenvectors of the matrix. Let me run just a single transformation, a single year in the forest. Can you spot the eigenlines? It turns out that the eigenlines are here and here. One of them has an eigenvalue of 1/2, which is less than 1. So the dots on this line move towards the origin. The other line has an eigenvalue of 1.5, which is larger than 1. So the dots move away from the origin. This already gives you a very strong hint about why we end up moving away from one line and towards another. I want to make sure that you realize what these lines mean. The horizontal and vertical axes give us the number of unicorns and trolls, but the slanted lines give us some proportion of the two species. This line, for instance, has a slope of 2, so it represents a situation in which there are twice as many trolls as unicorns. And that's what the system seems to be evolving towards in the long run. If I start from some arbitrary number of trolls and unicorns, say both 5, and I run the system on my computer a few times, you see that even after a few fairy tale years, there are twice as many trolls as unicorns. If you've ever wondered why there are so many trolls in the world, now you know. To understand where this long-term 2-to-1 proportion comes from, we have to diagonalize our matrix. Remember that we do this by changing our basis from the usual horizontal and vertical axes to the two eigenlines. Our matrix turns into a sandwich with a diagonal matrix in the middle. To run the system over many successive years, we have to start at some initial vector, such as 3,3, and then multiply it with our matrix over and over and over again. In other words, we transform the vector with successive powers of our matrix. Now watch this. As we take integer powers of our sandwich product, these pairs of sandwich matrices in the middle all cancel each other. One of the crusts is the inverse of the other, as always, and by placing them next to each other, we can make them vanish. What we end up with is just the powers of the diagonal matrix, with only a single pair of sandwich crusts at the ends. And that's great, because the powers of a diagonal matrix are extremely easy to calculate. I hope you see that you just have to raise the diagonal elements to the correct power. It doesn't get much easier than that. So, over the long term, the only thing that matters is the diagonal matrix. And now you also see why eigenvalues that are less than 1 slowly shrink towards 0 over time. The powers of a number less than 1 keep getting smaller. For a number larger than 1, the powers shoot off towards infinity. And that's why only the largest of the two eigenvalues dominates the long-term trend. The influence of the smallest eigenvalue just fades away over time. When engineers design a mechanical or electrical system, they can predict its long-term stability by looking at its eigenvalues. If any of the eigenvalues are larger than 1 in absolute value, the system will become unstable and break or explode. So it's kind of important to get this right. Eigenvalues are a huge topic with many more important and cool discoveries. I want to share a few additional details here. For those of you who want to dig even deeper, we have created a short extra video with more information about complex eigenvalues, block diagonal matrices, and how to exponentiate matrices. This extra video is available exclusively on Patreon. It won't be published on YouTube. So if you're interested, consider creating a Patreon account by following the link in the description. Okay, the first important detail is that the eigenvalue decomposition is possible only for square matrices. Eigenvectors have to stay on the same line, and this is only possible if you keep working in the same vector space. A rectangular matrix doesn't do that. It transforms from, say, a 2D space to a 3D space. Also, in order to calculate the eigenvalues, you have to compute a determinant, which is only possible for square matrices. In order to raise a matrix to a power, it also has to be square. A rectangular matrix cannot be multiplied with itself because the row and column counts don't match. So, as you can see, there are quite a few things that only square matrices can do. For rectangular matrices, we need a different but related approach called the singular value decomposition, which we will talk about in the next video. When your eigenvalues are real, the system will evolve around straight lines, like the unicorn example. But when the eigenvalues are complex, you will see spirals that rotate around the origin. When the length or norm or modulus of the complex eigenvalue is less than 1, the system spirals inward and ends up collapsing into the origin. When the modulus is larger than 1, the system spirals out of control. So again, to study the long-term stability of a bridge or a nuclear reactor valve, you have to make sure that its eigenvalues all have a length or absolute value less than 1. The ecosystem we've been studying is a discrete dynamic system. Every year we take one discrete step. However, in physics and engineering, you often have to model continuous systems instead. The continuous equivalent of taking successive integer powers is to take exponentials, and it turns out that the exponential of a diagonal matrix simply contains the exponentials of the diagonal elements. So what happens to a continuous system in the long term is determined by the exponentials of the eigenvalues. That's why this time we no longer care whether the eigenvalues are smaller or larger than 1. Instead, we care about the sign of the eigenvalues, because positive exponents make our system explode to infinity, while negative ones slowly settle down. So you have to make sure that you use the correct analysis depending on what kind of system you're investigating. Some types of systems behave very differently than others. The devil is in the details. And finally, remember that we are looking only at linear models here. As soon as you introduce higher powers of x or y, things start to look very different and weird and exciting. Nonlinear systems, such as this parabola, can produce unpredictable chaos and intricate patterns that are often incredibly beautiful, but also very hard to understand. Instead of evolving along straight lines or simple spirals, the system can jump all over the place, and when you try to predict what will happen to it in the long run, you get shapes with infinite details and self-similarity. A linear system could never produce such daunting detail. Don't forget that there is an extra video exclusively available on Patreon. In the meantime, I'm gonna leave you with this animation of complex numbers dancing around in the Mandelbrot set. This is a quadratic system rather than a linear one. Points that start inside the black region in the middle stay trapped in that region forever. Points outside will eventually escape to infinity, but it may take a long time and a lot of jumping around. This gives you an idea of how much more complicated a nonlinear system can be. Its behavior in the long run is much harder to predict than the simple linear ecosystem of unicorns and trolls. Enjoy the animation, and please take 2 seconds to subscribe and to like this video. Thank you so much. See you later.